In the night sky, a bat emits rapid, high-frequency sound waves to track and intercept an insect in midair. Upon hearing these ultrasonic pulses, a moth drops from its flight path to evade capture. Biologists and educators often classify this dynamic as a strict co-evolutionary arms race, a contest of perfectly matched measure and countermeasure. A true co-evolutionary arms race requires reciprocal, species-specific adaptations. These traits do not fit that definition. Most adaptations that make a bat a better moth hunter also make it effective at catching many other types of insects. The engine of this interaction is the life dinner principle, a concept introduced by biologists Richard Dawkins and John Krebs. If a bat fails to catch a moth, the evolutionary cost is a lost meal. If the moth fails to evade the bat, the cost is its life. This asymmetry in survival stakes drives opportunistic evolutionary trajectories. Predator and prey are not locked in a perfectly matched one-to-one dance. The fossil record shows exactly how disconnected these trajectories are. The order Lepidoptera, comprising all moths and butterflies, originated roughly 150 million years ago. They established their nocturnal flight patterns long before their primary mammalian predators existed. Early bats only took to the air between 60 and 95 million years ago. The pivotal hunting mechanism, laryngeal echolocation, emerged much later, around 50 million years ago. For an insect population accustomed to the dark, the arrival of a flying mammal emitting high-frequency sound acted as a novel predatory filter. Insect ultrasound hearing was a reactive defense to a new mammalian sensory modality, rather than a simultaneous coevolution. Biologists are still mapping the exact origin of that mammalian sensory modality. This phylogenetic tree illustrates the single origin hypothesis. Echolocation evolved once in a common ancestor and was subsequently lost in the Pteropodidae, or fruit bat, family. The dual origin hypothesis presents a parsimonious alternative, where echolocation evolved entirely independently in both the Yinterochiroptera and Yangochiroptera suborders. Combining powered flight with this active sensing system allowed bats to track and intercept prey in total darkness. Because echolocation requires broadcasting high-energy acoustic signals, bats inadvertently flooded the night sky with tracking information for any organism capable of hearing it. This predation pressure forced a convergent rewiring of insect nervous systems on a global scale. In this biological system, an ear is a functional specialization for high-frequency sound perception, characterized by its purpose rather than common anatomical descent. Insects already possess internal sensory structures called chordotonal organs. These are stretch receptors that monitor the insect's own physical movements. Selective pressure thinned specific areas of the insect exoskeleton into vibrating membranes, or tympana. The internal chordotonal organs were then rewired to transduce external acoustic vibrations instead of internal movements. Within the order Lepidoptera alone, this evolutionary workaround occurred independently at least 6 separate times. These events resulted in auditory organs manifesting on arbitrary body segments, from forelegs and abdomens to thoraxes and mouthparts, depending on the insect order. Insect hearing is a masterclass in evolutionary opportunism, converting internal hardware into acoustic sensors wherever structurally possible. The moth ear operates through a minimalist anatomical design, contrasting with the complex mammalian inner ear. In the noctoid moth ear, the tympanum is backed by hollow air sacs. Auditory receptor cells connect directly to the inner surface of the tympanic membrane to detect vibrations. Because all auditory afferents share the same frequency tuning, moths cannot distinguish between pitches of ultrasound. Survival relies exclusively on decoding the amplitude and the pulse pattern of the incoming sound waves. This chart plots the neural firing rate of a moth's ear against decibel levels. It shows the ear is innervated by a small number of auditory afferents. The A1 neuron is the most sensitive receptor, firing at low decibel levels to detect distant bats. As sound intensity increases, the A1 neuron reaches its maximum firing capability and plateaus. Because of a 15 to 20 decibel threshold difference, the A2 receptor begins firing just as A1 maxes out, continuing to encode the increasing volume. This staggered threshold generates a 40 to 60 decibel dynamic range for intensity discrimination from two cells. This stepwise neural coding acts as a distance calculator. allowing the moth to trigger stage-appropriate evasive maneuvers without the metabolic cost of complex neural processing. Once insects evolved ultrasound hearing, selective pressure returned to the bats to bypass these new auditory defenses. Some bats counter-adapted by shifting their echolocation frequencies outside the typical sensitivity range of moth ears. Others utilize stealth echolocation, dropping the amplitude of their calls so the moth's A1 neuron cannot detect them until the predator is within striking distance. This sustained predation altered the survival strategies of entire insect lineages. Auditory defenses alone were not enough for all groups to persist in the night sky. The pressure of bat predation eventually drove some previously nocturnal insect lineages into diurnal lifestyles to escape echolocation altogether. This interaction represents a sprawling, asymmetric biological escalation, rather than a neatly matched co-evolution. The Bat-Moth system shows how universal physical constraints, like high-frequency sound propagation, drive the evolution of precise neurobiological solutions over millions of years.